works in terms of your understanding of the concept. Let's move to 3 dimensions. Classic, straightforward question. Given 2 points in 3 space, let's come up with the vector equation of the line passing through those points. This is a 3-dimensional setting on a 2-dimensional space here, or surface. Crude idea, A would be sort of over 2, drop down 1, come out 2 in Z, that's what that's saying. B would be over 3, drop down 2, go back 1. So this is kind of just crudely approximating where these points would be, just to give you a kind of a conceptual sense. Well, we want to come up with the equation of this line that's dotted in red. Its ultimate result is right here. That is the vector equation of a line. It's based upon this basic general structure here. So what do we need? We need to talk about the infinite x, y, z ordered triples that are now on this line, because we're in 3-dimensional space, right? Those x, y, z ordered triples, each of those is characterized by first get yourself up to or onto the line from the origin. Well, we could either go from the origin to A, because that would be, in fact, that's the point that I chose, or we could have actually gone from the origin to B. I just chose not to use that. So we do have a known point on the line, namely that point, and its position vector is right there. So that's the sort of OA bit. There it is up there. And then we say, well, where is the vector that's out here somewhere or over here somewhere? That's exactly parallel to this line, because we need this direction vector called B. Well, the only thing we can do is actually construct a vector between A and B. So you see the construct here of vector AB, and even though it's embedded right in the line itself, it certainly would be considered parallel to the line, or a direction vector with respect to that red line. So the classic way to get yourself from A to B is to go from A to O, and then add to that from O to B. So that's what's going on here. The negative of OA is how you go back from A to O, and then you're adding to that OB. So that is the way you move from this point in a vector sense to that point, right? So that becomes the direction vector for that particular line, and there it is right there. That is a classic looking form to the answer of what is the vector equation of a line in 3-dimensional space, because it defines relative to some x, y, and z. There's an infinite number of x, y, z's on that line right there. It defines them in terms of some what's called a parameter t, which is a little bit abstract to us now, and we'll kind of get to what that means as we get into extending the idea of that line that we just came up with in red. So that's the same line. Now as it intersects this other line that's in gray, and I've just given you that. So this we just constructed, and this I'm saying given there's a second line in play such that the second line and the first line cross right at B. Let's see if we can actually find the position vector that's in green here that describes, sorry, not at B, because B's out here. It crosses at some point P right here. Let's see if we can actually come up with the position vector of that, that point that represents the intersection. Well, if you think about it, the position vector of that precise point right there is not only a point that's on the red L1, but it's also on the gray L2. And so if these x, y, z position vectors for any r on the red line, there's an infinite number of them, of course, and these are the x, y, z points described by this one. Well, there comes a unique place where, in fact, each are the same. And so it should make like intuitive sense to you that we're taking this line here and this form of the line here, and we are equating it to the other form of the line because they really only meet in one place. And so we're trying to find the exact x, y, z coordinates that in terms of where that meeting actually takes place. And so if you play out the sort of arithmetic stroke algebra on this, we form a system of equations, right? Because 2 plus 1t, that's right here, is equal to 3 minus s. That's here. So that's kind of saying x equals x. These middle ones is where negative 1 minus t, when you multiply, that y value has to exactly match up to this y value, which is negative 1 plus 2s. And then, of course, 2 minus 3t for the z position here has to exactly match the z position over here, which is negative 6 minus 2s. So here we're confronted for the first time with some kind of a system, 3 equations, equations 1, 2, and 3, where there's actually only 2 unknowns. How do you handle this? You solve for the 2 unknowns using any 2 of the equations, and then you have to confirm the s and t values that you find using any of the 2, and I'm going to use the first 2. You confirm them into the other one to make sure that it balances it out. And it might not balance it out, but that's a story for another podcast. So I've taken equation 1 and equation 2 and said, okay, 2 equations, 2 unknowns, namely s and t, that's manageable. Solve it by, I use the elimination method by just adding the 2 together. So if you notice that these t values, if you were to add the 2 separate equations together, these t values will cancel out. So negative 2 plus 1 is 1, and negative t minus t adds to be 0. That's why it's gone. 3 plus negative 1 is 2, and negative s plus 2s is positive s. Lo and behold, we've eliminated t from the system. Bring that guy over, and it looks like s is negative 1. Back substitute by plugging s of negative 1 into, I just grabbed the first equation. So 2 plus t, that's right here, becomes 3 minus the negative 1 that we just found, better known as 4. Subtract the 2 from it, and we get that t is actually equal to 2. So again, you choose whichever 2 of the 3 systems, you choose whichever 2 of the 3 equations you prefer, solve the system, and then make sure that these 2 values check by giving you equality in the third one. So when you check out equation 3 and you plug t of 2 in there it is, s of negative 1 in there, it looks like you get a perfect balance that negative 4 is equal to 4, and that confirms that these particular values are giving you, as it turns out, the place where they meet. Because if you plug that value of 2 in here, because we're talking about, right, we're back here where t is 2 and s is negative 1, you're finding very, very unique and specific what's called parametric values, parameters, the 2 and negative 1. If you see, you've got 2 plus 2 being 4, you've got negative 1 minus 2 being negative 3, you've got 2 minus 6 being negative 4, and lo and behold, the s of negative 1 here gives you 3 plus 1, because you're multiplying here, that's 4. Negative 1 minus 2 when you multiply, that's negative 3. You can see the match that's unfolding, negative 6 plus 2 is negative 4. They exactly match. So these 2 particular unique values land you at that point, which lends itself to this green position vector, which is exactly where the 2 meet, because you've forced the system to, by setting them equal to each other, to actually meet there. The last thing, and then we're done, is to pick up on the idea of if we know how to find the angle between 2 vectors. So let's say there's just 2 vectors floating in space somewhere. We saw that the scalar product, also called the dot product, is a function of cosine in between them. We could actually find the angle between those 2 vectors. Well, now what we're saying is the way these lines are defined, that there's some direction vector that's either embedded in the red line or parallel to it. That's right here. And then there's some other direction vector that's parallel to the other line. That's right here. So if these 2 vectors are parallel to the red and gray lines respectively, then of course the angle between these two lines themselves are just characterized by the angle between these two direction vectors. And so that's the final point to be making. And so here's a classic setup of the scalar product. So that would be the length of this vector right here. And note once again, I've ignored the negatives because squaring negatives is the same as squaring the positives. Here is the length of the second direction vector related to this one. So that's sort of v1 times v2 in terms of their magnitudes or their lengths times the cosine of the angle between them. So that angle would be somewhere right in here. And then the other form of the scalar product was simply multiplying the two x's. That's right here. Add to that the multiplication of the two y's. That's right here. Add to that the multiplication of the two z's. That's right there. You should be able to confirm that when you do the arithmetic on this and use your inverse cosine, that this ends up being 72.5 degrees. That's it. Thank you.